Hello and welcome back to our AB1202 Statistics and Analysis Week 6 tutorial. Today we have a brief but very important agenda, and that is to talk about the idea of sampling and what is the meaning of central limit theorem. How do we apply it? What is it all about? Right, and you might have seen this acronym CLT before. So let's begin with sampling. Just to bring out the whole gist of even talking about this concept, sampling, we do sampling because the goal, right, is to find mu, the population mean. Of course, with all the data that we collect during the sampling activity, we can also find or attempt to estimate other aspects, what we call parameters of the population. Parameters are simply one number summary of the many numbers or measurements in the population. For example, in a city of, let's say, 200,000 people, yeah, that's not a very big city. Maybe we should call it a town, right? So it's a small town of 200,000 people, and that's a lot, right? Even though it's not in the millions, it's still a lot of people. Now, every person has a lot of data or measurements about the person. It could be the, body related, height, weight, amount of fat the person has on the inside the body, and bank account balance, the salary, yeah, monthly salary, annual salary, because with bonus it can be more, and so on and so forth. As you can imagine, there's like whole bunch of data associated with one person. So with 200,000, it means if one person has easily 100 different measurements, then 200,000, we're talking about 200,000 times 100, yeah, different sets of measurements. So if we want to find, let's say, the average of everyone's income, that's the population mean income, that's the mu. That's the mu we're talking about. So that's the average of everyone's height. That's another population mean, but mean of the height. Yeah. Okay. So can we do that? Can. If we have a lot of time, money, and technology, and everything is in our favor. But usually, one or more of these will be no. For example, we don't have the time to measure 200,000 people one by one because you're a one-person team. We don't have the resources, right? So if you have the time, then you will basically get outdated data, because after 2 years, finally, if you can finish 200,000 people's measurement, their income will have changed. Some of their heights will have changed. Some of their weights will have changed, right? So your data is outdated and it becomes void, and you have to remeasure again. So you can never really find mu at that point in time. Yeah, you get the idea now, right? So it is difficult because we don't have the time, money, patience, technology, because I only have a Casio calculator that can add and subtract maybe 20 numbers at most, right? So how to add and subtract 200,000 numbers, right? Whether the numbers are for height or weight or for salary or whatever else. So you can see the difficulty. Yeah? Just to ask a simple question: what's the average salary? What's the average monthly income of this small town of 200,000 people? So what do? We sample, right? So that's the idea. You might have heard of it, and we intuitively do that. Well, I just ask my two neighbors, right, and then measure their height, 1.5, 1.7 meters, take the average, 1.6 meters. So I then declare that 1.6 meters is mu, the population mean height of all the 200,000 people. Okay, so two things. Is it accurate? That means, is it correct? No, not really. Right? Of course not, because you haven't seen the rest of the 199,998 people, right? You haven't really touched the reality. You haven't really measured them. How dare you say that they don't make a dent at all to your estimate of 1.6 meters? Huh? So, is it accurate? No. Almost always no. Uh, but is it approximately right? Yeah, yeah, you cannot be too far off, right? Because you are actually spending some time and effort to measure two of your neighbors, 1.5 meters, 1.7 meters, and then at least these two measurements are correct, right? And so when you take the average, it might not be far off. Let's say the actual average is 1.65 meters. But because your neighbors are just random persons, you pick them, you might just have that random chance of encountering a relatively taller person, relatively shorter person. Take the average, it cannot be too far off. You see that? So that's the logic and argument behind statistics when we do sampling. So it cannot be too far off. Then next thing is, that's it. It's just an estimate. We say, yeah, it's just an estimate. But the advantage is it is very low in resource requirements, right? We just take the effort of measuring two persons, and that's all. Yeah, we don't need to spend a lot of time. We don't need to waste a lot of money. We don't need an advanced R or Excel or Python to do the calculations. Just a plain old big button Tauke calculator will do, right? So we can just press the calculator and quickly, right? Time-wise, it's very convenient, and we already have a good estimate. So if that serves the purpose, we are often very contented with this. What happens if it's a scientific kind of study, right? So, or a very important business decision, you need higher precision. Okay, so accuracy is not always guaranteed, but precision, the number of decimal places you can at least say is reliable, right? That's the precision. So if we need higher precision, higher reliability, what should we do? Well, as you can imagine, we do have a parameter, a controllable norm here, which is the amount of effort we are willing to put in. And translated into statistical speak, that's our sample size. Okay, so sample size. So first thing first is the goal is to find mu. And the next associated notion is we control the estimated mean all right, control the reliability, right? Precision and reliability of the estimated mean x bar by sample size n. So that's our lever, right? So that's our control knob to tune to have higher precision but higher cost in time, in money, in budget, in manpower, in technology, or smaller n. Okay, so lower financial commitment, manpower, technology requirements, but then of course precision reliability also goes down. So one has to kind of take a sort of trade-off between the two. Yeah, so that's the situation we have. Now, just to give a feel of how we interpret this sample mean, all right, we use it as a point estimate. So this x bar is called the sample mean. As opposed to the actual population mean. So this actual population mean, for example, could be a number 1.65 meters. I put in small font because we are not supposed to know. We can never know, in fact, right? We will never know unless we spend the whole, the whole town's 10 years budget or whatever it is, right? So it's impossible to get that kind of agreement. It's impossible to know. But X bar is possible to know. It is always knowable. Because if it is costing too much to know, we simply reduce n small enough, right? In the extreme, just two measurements. And then we can understand and calculate x bar, and then we point estimate. We get a number, for example, 1.6. And then we point estimate. So this action of taking the value of x bar and assume that mu is 1.6 when actually mu is 1.65. That is never known, right? So this is called point estimation. The copying of x bar to mu. So that activity, that copying, is called point estimation. Because we cannot really mathematically correctly say mu is exactly 1.6, correct? That's wrong, because nobody knows. How dare you say that, right? So we will say that x bar 1.6 that we do know exists and it's real is going to point estimate mu, so that in all our so-called human communications from there on, we will just say mu equals to 1.6. But then should the need arise to be much clearer, is it true? Is mu actually 1.6? Because I, another scientist or neighbor, got two of his neighbors and take the average. That x bar that was found is 1.63, is not 1.6. Right, so now you are being challenged. And I heard you say mu is 1.6, but my mu is 1.63. So there's a problem, right? Mu cannot be two numbers at the same time. So we resolve this by saying, well, both of you are right? Because when sample size is the same, n equals to 2, you may get many repeats of the same sample size, right? Just like you did with two neighbors, and your neighbor, right, maybe down the street, also did the same experiment with his two neighbors and take the average. And you can imagine the average thus found cannot be the same as your 1.6, right? So the person got 1.63. So both of you will try to point estimate your x bar to mu, but that is not contradicting. So both of you are doing the same point estimation activities. That's how we say it. And both of you are going to assert without proof that mu, the population parameter that has only one number, is, to you it is 1.6, to that neighbor is 1.62. Okay, so that's why sometimes that for students like yourselves beginning to learn this concept, you might get a bit of confusion. How come we can get so many numbers for mu? And it seems to be all correct. And actually, one has to clarify, these are actually point estimates of mu. And then it won't be wrong because everyone is guessing. Another layman way of thinking about point estimation is guessing. Basically, we're all guessing in the official manner. So this is acceptable. This guessing is acceptable. All right. Yeah, because even in courts of law, we go by probabilistic judgment, because this kind of assertion is acceptable so long as n is reasonably large enough, right? So that's how large is large, of course, is then determined by the actual context and by the court. And here, suppose if we talk about not about height, but rather DNA matching, then yeah, we might have to perform sampling as well. So we'll sample a person's blood, right? By one drop. But one drop has got many, or maybe several milliliters, which will have a lot of drops. And if one DNA analysis says 95% match, that's not very high, not high enough, right? Because typically it can be 99.999%. Or 98%, or so if one particular sample, one drop of the blood performing DNA analysis shows 95%, another analysis of from the same two people can be 98%. and then yet another trial, that means sample size now n equals to 3, it can be 99%. So so then you probably want to take the sample mean of these percentages to estimate what is the real, true, correct population mean of the matching percentage of these two persons. Yeah, so it can be very serious, right? Are these two people related, or is this person's blood the same as the blood stains found in the crime scene? Yeah, so then the court of law will then determine, okay, so the sample size is how many times do you do the analysis? 5 times. So that is quite a lot already, or 10 times, right? So that after repeating 10 times, our analysis shows that the average match percentage is 98.99%. Oh, then then it is very convincing, right or not? Yeah. So if the accusing lawyer says we did only one analysis, or we did one analysis and it shows 95% match, then the defending lawyer can say that's a sample size of 1, right? You might have just accidentally taken a kind of a blood sample that is matching quite well, and so if you try again, it may be 80, or maybe it may be 30, right? It may be that the blood stain found in the crime scene has just 1 drop of blood suffered by the defense, and out of injury, not out of criminal behavior, right? So the defense lawyer can say a lot due to the very low sample size of 1. And so no, the plaintiff lawyer says, yeah, we did 10 times. After repetition, after using almost all parts of the blood stains found on the crime scene, we get this. So you can see that this finding mean can be, well, as silly as finding the average height of the town, or as serious as going to court of law, right? And determining whether a person is guilty or not, whether two strangers, right, are actually having blood relationship or not. Yeah, so this can be quite serious. Okay, so just to understand the concept a little bit more, yeah, so let's try to manually, as you know in my video sessions, right, manually simulate what is meant by sampling. So again, I like to talk about the town of 200,000 people. And let's just make it a little bit more interesting. Let's talk about money, right? So the town has all of them has wallets, right? So they have wallets, and each of them has some money in the wallet, right? Not the bank balance, but the actual money carried in the wallets. So each wallet, let's just make everything simpler because we don't want to make it very complicated. Then I'll have to activate my R or computer to calculate this. Let's just make it very simple. The town people can have either $2 in their wallets or $3 in their wallets. So X is the number of dollars in their wallets. And we now know that the sample space of X is $2 or $3. No other dollar numbers are possible. Also, no such thing as a $10 note, $50 note. Let's just imagine that's possible, but we can easily extend to those later on. So let's not distract ourselves with, let's say this all real number, any notes is possible. While that's more realistic, it is confusing. And because we want to make it easier for calculation without distracting ourselves with all the numerical calculations, let's just say that at the start, right, they have equal numbers. That means 100,000 people hold $2 in their wallets, and 100,000 people hold $3 in their wallets. Correct? Yeah. Let's just say that's correct. I shouldn't be asking whether it's correct. Okay, so that's our scenario. And then I can ask you guys, right? What's the population mean? So quietly, right? Quietly in this dotted line bracket, quietly the mean of X, that is mu itself, is equal to, I'm sure you agree with me, it is 2.5, correct? Yeah, it's 2.5. Okay. So this is x, but x has no such thing as 2.5. So you cannot draw 2.5 inside. Although you can just make a marker here and say 2.5 is mu, right? But number one, 2.5 is not in the sample space of x, correct? Because nobody has a 50-cent coin. It's not manufactured in the town. It's not possible for anyone to carry 50 cents. Number two, um, this is mean. This is mean of x, right? And this is mu. This is a number, right? And it has a real part to it, a fractional part to it, and so it has no place to sit. You can draw the mu here, right? And it has no place to sit. And number two is, of course, we don't really know mu. Mu is unknowable because too many people, right? Okay, so that's the context. And what we do now is we are one of the 200,000 people, and we would like to know without asking everyone, because look, I mean, if you ask strangers, they won't tell you how much money they have in their wallet, right? So, but we would like to know. We would like to know what's the average of everyone's wallets in this town of 200 people. So what do we do? Well, very simple. You can imagine you are one of the 200,000 people and you want to know. So what would you do? You will randomly ask, let's say n equals to 2, right? A sample size of 2. So a sample size of 2, you will get, you can get such combination as 2 and then 2, right? First, you get a person who has $2. How much money do you have? $2. Second person you ask, $2. And this 2, you can permute them and you still get back 2. It's indistinguishable. I mean, the two people that you ask, they are distinguishable. But when you kind of reduce them to a wallet number, they both have 2 and 2. So it doesn't matter whether you ask the first person first or second person first, right? They will just give you this collective response of 2 comma 2, right? So once you get that, your X bar is going to be $2 because average of 2 and 2, 2, right? And what happens if you get that a lot? Then you will get a bar on top of 2. So the average is 2. Average is 2. But that would not be the only case. You could also get 2, 3. If you get 2, 3, then first of all, the X bar is going to be $2.50. And number 2, now we may see a difference because the first person you ask is $2, second person $3, but it could also be 3, 2, right? So these two both contribute. That means there is twice as frequent encounters of 2, 3, 3, 2 combination. So if you physically ask them, there's a sequence. There's 2, 3, then followed by 3, 2. But if you don't care about the sequence, then you just have a combination, and the combination produces an average of 2.5. In other words, 2.5 will have twice as high a probability as 2 to occur. So we'll see 2.5 more frequently. Yeah. And of course, if you randomly pick 2 people, that 2 people can also show up as 3, 3. Not impossible, right? And quite readily. And then that will give us an average of 3. And if you go by this, you can already see that, first of all, right, this is a sample space of 2, 3, and 2.5, because these are actual numbers that X bar. Now, I'm writing a big X bar here because I'm going to repeat this 2 times, 3 times, 4 times randomly with various pairs of people and neighbors. I might even go further into the town center, busy street, busy hour, to randomly hijack or stop two people and then ask them how much money do you have in the wallet. I'll give you a lollipop, right? After you answer my question. So I will do that repeatedly many times to obtain many numbers, many sample means. Right? These are called the sample means, correct? Yeah, X bar. So I will now get many sample means with the plural here, right? And I will get any one of these, maybe 2.5 twice as frequently as 2 and 3. But eventually you will agree with me. Yeah, I hope that we will see a dot here, a high up dot here, a lower, roughly speaking, half as high. But of course, if I do it, it cannot be infinity. It's probably a repeat it 100,000 times, right? And you can imagine that's already theoretical. Physically, a person might not want to do that unless someone holds a gun to your head, right? So that already is good enough to show up as this. Okay, so number one, we have to draw these numbers, the X bar numbers, not on the X itself, because there is no, will give the wrong message that as if X can have 2.5 as its possible outcome. But that cannot be. Nobody holds $2.50. Correct or not? So the X bar, 2 is okay. That's the confusing part. It might encourage us to just draw the X bar over the X axis, when actually X bar does not sit in the X axis, the capital X histogram. It sits in its own X bar histogram. In fact, I should put an X bar 2 here. This 2 typically is not shown in textbooks or even your lecture notes and most discussions, because they already explain that having a sample size of 2, we're going to do this. So the notion that sample size is 2 will then result in this histogram is already explained, right? So the 2 is already known. But as I'm going to try again with n equals to 3, I want to make a distinction. No? So this is the histogram, or in this case, the distribution shown when we do the sampling activity with sample size 2. First of all, this diagram, the X diagram is the wallet, right? So we call this the parent distribution. In this case, I'm measuring the wallet amount. This is the sampling distribution. This is the distribution, that means another word for distribution, histogram. The histogram, that is the result of repeatedly doing it infinitely many times, this sample mean activity. So it's called, the full name is sampling distribution of sample mean. Some textbooks, after introducing this long word, will refer to as sampling distribution. Then that does mean that we're talking about the X bar. So anytime you see sampling distribution, not sample mean, sample mean is the number. Sampling distribution is a histogram, right? And the associated random variable almost always, right, will have a bar here, unless you are trying to be weird and say let W equals to X bar 2. That's not very descriptive, right? So we'll rather stick with X bar 2. Number one, it suggests that the source measurements come from the parent called X, right? So X. Bar is to say that what we do is to combine these sampled measurements using average. Imagine this is not combined using average. We take the maximum. Then this is 2, then this is 3, then this is 3. Correct or not? We can do that. And that would result in a lopsided 2 is very low, 3. And that is another distribution. That will be sampling distribution of sample max. But no textbook talks about that, because we don't do that, and that's not very helpful. But then it can be invented, right, in a mathematical virtual world. We can do that. Then find some meaningful use of that. That's possible. But here, this sampling distribution of sample mean is what we are very concerned with, and we are very interested to know more, right? So any X bar n, right, n be 2, 3, 4, 5, right, they are all called sampling distributions of sample mean. So typically, whether it's in the textbook, In the exercises, in exam, in quizzes, that question only has one sample size. That's why there's no need to say x bar n. There's no need to say x bar 5, x bar 12. Yeah, there's no need because the n is understood. But that's what I'm going to do now. I'm going to try n equals to 3 and see what happens, right? So the sample means are going to be, first of all, I'm going to definitely produce a new sampling distribution of sample means, and it will be x bar 3, right? Because now it's based on sample size 3. Why do I need to do that? Because the outcomes are different. For n equals to 3 means I measure from the parent distribution, the source here. If I pick any 3 neighbors, 3 people from the top, what kind of numbers do I get? Well, let's just list it out. I can get 2, 2, 2, right? I can get, and that's all, because if I permute the 2's as a collection in order to calculate x bar, it doesn't make a difference. So I don't care. Order doesn't matter, right? So if I get 2, 2, 2. But if I get 2, 2, 3, then it does induce these various other permutations that basically are treated as one, right? So basically they all result in x bar equals to, what is this? 2 and 1/3, right? Because there's a 1 here to be divided by 3. So let's just abbreviate. It's supposed to be 2.333333 all the way. And we can also get 2, 3, 3, and this will give rise to 3, 2, 3, 3, 3, 2. You can actually list it all out because all these will give rise to 2.6666667. Right? Yeah, okay, so, and finally, if I get any 3, I will get 3, 3, 3. And same as 2, 2, 2, this gives rise to just 3. And this 3 times, right, as many different permutations as we can get from the second and the third listing here, implies that the histogram will be similarly shown, because we are going to add stack on top, right? Every time we get a 2, we are going to get a 2 here and put a Lego toy block on top, right? And every time we get a 2.33, we will put another Lego toy block on top, and so on, right? But since we're getting 2.33 3 times as often, we're going to stack the Lego toy blocks 3 times as high, right? Because that's basically a result, a necessary result from our analysis. Whereas these two extremes, 222 and 333, they will just sit somewhere lower, 3 times lower. So that's going to be over here. All right. And these 2 guys will be 3 times as tall. Now, a few things are already starting to show that with n equals to 2, we get this, which is not the same shape, right? And even sample space as the parent. Number 2, when n increases, you get more and more refined shape, right? And again, it's different from x bar 2, x itself. X itself, you can take it as x bar 1. Is equivalent to x bar 1, yeah? Because you take any single measurement, which is also the average of itself. So it's like sample size equals to 1, right? So this is n equals to 1, n equals to 2, n equals to 3, and n equals to 4. You can imagine keep doing this, right? And it starting to get more complicated. But the pattern is easy to see. And what if it is uneven? More people have 2 than 3, yeah, because richer people, they are less in proportion, right? So if this is 60% of the population, this is 40%, then it will start to show differently. Then you have a Y, right? You have a Y, a different town, Y, that has 60% of population having $2, 40% having $3. Then of course the Y bar 2 will show differently from X bar 2. Okay, so we're beginning to do, we see this. Yeah. And this is the painstaking way of building up the sampling distribution of sample mean. This is when n equals to 2, when n equals to 3. And if you keep doing, all right, for sample size n, and n is large. Remember n is large? What is the meaning of n is large? In statistics, we say n is large when it is 30 or more. Now, 30 or more, you might heave a sigh of relief and say, wow, thankfully it's not 30 million, right? Yeah. But 30 can be also very large, scarily large. Because if you're saying, let's find, for example, late stage cancer patients to try this new drug, and we measure the response, the healing rate, or the cancer cells being cancelled, being controlled by the drug. We measure the rate of recovery. And if you want to do that, then it's rather difficult, right? It's because to find late stage cancer patients, then it has to be also hopefully in the same country, so that the medical clearance procedure and clinical trial approval, all these procedures are followed and can be done, can save some time in getting approval. Because if it's in another country, then there may be a little bit more delay. Then you need the patient to agree voluntarily, this is new drug, no guarantee, it might even worsen your cancer, do you agree, right? So it's difficult. So to get one patient is already difficult. Sample size 1 is already difficult. Talk about 30, right? But that's the statistical guidance. You need to have 30. If you have 30, then what happens? Here comes CLT, right? Okay, so if you get 30, then the dots, well, we still have 2. We still have 3 as the limits, because so long as you are doing sample means, it cannot average to beyond 3 or below 2. All your numbers are between 2 and 3 right now, yeah? So no matter what is the proportion, the numbers will have to hover in between 2 and 3. But as you can see that when n is growing, the resulting values start to increase. N equals to 2, we get 3. N equals to 3, we get 4. So when n equals to n, whatever it is, like 30, we get 31 values, right? So we get a lot of numbers. And when n is 100,000, we get 100,000 markers inside. It's almost indistinguishable from a real number line. Of course, mathematicians will say, no, that's totally different. There are infinite numbers between 2 and 3. And 100,000 is nothing compared to infinity. But practically speaking, 100,000 different numbers in between, that's like indistinguishable from a smooth continuum. And what happens is you will get the similar idea. Those numbers in between will tend to be higher, right? And those at the edges will tend to be lesser. Imagine, for example, n is 100,000. Because n large, right? Yeah, you can be just a mental experiment. N is 100,000. How to get a 2? How to get a 2? Well, you better be so lucky as to be able to always get the 100,000, to always get a $2 wallet person for 100,000 times. That means every time you pick, you better be so accurate and well guided to always pick the person with $2 in his or her wallet. That's like tough, right? Very rare, not impossible, but it's almost like asking for the planets to align in a single line as you look up the sky, right? So it's very, very rare, though not impossible. So you can now imagine that this point, we can do the calculations, but I hope you agree with the logic and a little bit of an animation here, right? To go from n equals to 1, 2 and 3, they are sky high. To n equals to 2, they drop by half. N equals to 3, they drop by 1/3. N equals to 100,000, they drop by, like, safe to say, a good guess would be they drop by 100,000th, right? So they go from 100,000 to 1, something like this. So very, very low height. Then in the middle, it will be very, very many multiples taller than the edges here. Huh? So of course, we scale down to do this. All right, and because it's almost indistinguishable from continuum, we don't need to draw many bars. It's just going to be like almost looking like a smooth line. All right, like this. And this is beginning to look like a normal curve. All right, this is beginning to look like a normal curve. Of course, it's not normal. Why? Because the tails are hard locked at 2 and 3. You cannot go beyond 3. You cannot go below 2. Whereas a true bell curve will extend to positive infinity and extend to minus infinity. So strictly speaking, we cannot say this is a bell curve, but then everything else inside 2 and 3, it's looking very much like bell curve. What does that mean? When you overlay a bell curve, a true bell curve on top, it will be hugging so closely to this line that you cannot see the true bell curve. So that our blue actual sampling distribution overlies on top of the true bell curve. And only the tails are visible because our sample space must be strictly between 2 and 3. But then the tail is so low, that means it's so having such a low area that it's like 0.00, like 20 zeros later, then you have a 1 or 3 or 9. And so it doesn't matter, right? No practical speaking, there is no concern to assume that our blue curve also extends to infinity. Really no concern. Either way works, right? To assume that the bell curve gets truncated to 2 and 3, or our blue curve, our sampling distribution, can have a 0.0020 zeros, 30 zeros chance of going to minus infinity. That's okay, because when we say that, then we say that, well, our sampling distribution of sample mean, at first, not a bell curve, but when n is large enough, it is a bell curve, right? By ignoring the tail a little bit, we say this is n. So x bar n becomes or follows normal distribution. This is the key contribution of okay, this statement. Let me finish the statement. As n goes to infinity, so n large is good enough, but as n goes to infinity, more mathematically, strictly speaking, then n x bar n does become n, normal distribution. So here we have what is it? Okay, so CLT. So CLT tells us the shape of the sampling distribution of sample. This is the key contribution by CLT. The shape becomes looking like normal. That's all. But to prove it is very complicated, because here we have made a lot of simplified assumption. We're saying it's only 2 and 3. We're saying, it's 100,000. We're making it easier to mentally accept this, gradual transformation, right? But you got to also make it work for any distribution. When this is lopsided, when this is triangular, when we start off with some other different combinations, and the numbers may be from 0 to 20, right? Or real number axis, or whatever it is. And CLT still works. So we start with a parent that is not normal, right? So notably, not normal. Yeah, so our parent starts off as not normal. That sounds strange. The parent starts off as not normal because it's not a bell shape. Yeah, so but then when we perform this repeated sampling activity, and as we increase n you don't have to progress from first you do n equals to 2, then n equals to 3, right? You can jump straight to n equals to 30 or 40, right? So that's because we know about CLT. CLT tells us to how big an n should you jump so that your sampling distribution approximates very well a normal curve. Oh, then reading central limit theorem, we know the magic number is 30. So we start with 30. So that's the contribution by CLT. CLT then gives you a visa, a guarantee that your sampling distribution of sample mean will be very much looking like a normal. So much so that you might as well just say, in all practical contexts, that your sampling distribution of sample mean for n sample size being n and n is large is normal. Okay, so here, normal. That's the beauty and contribution by CLT. Again, let me say that's just the shape. CLT tells us about the shape or gives us this guarantee about the shape. Now, what's so big deal about the shape? Other than it looks more beautiful, it's normal, it's more symmetrical. And even if you started off asymmetrical, right, you have a lopsided kind of parent distribution, not normal. Eventually, it will look symmetrical. It will look normal because normal has to be symmetrical, right? So what's so big deal about this shape thingy, right? Well, because if it's symmetrical, then number one, you can use various functions in Excel, in R, in Python, such as pnorm and qnorm in R, to calculate the numbers inside this sampling distribution of sample. Remember, we can measure, we can calculate, we can point at in real life, right? Anything about this X bar sample space, whether it's X bar 2, 3, n. We cannot, right? We cannot measure or point at the mu in the parent sample space. Where's the mu? We don't know. We may guess that it's between 2 to 3, but there are infinite possible numbers between 2 to 3, right? So our best way to interpret what we measure is on the histogram, on the distribution of sampling distribution. And that's why we want to analyze and point at and calculate and talk about the shape of the sampling distribution. So now by CLT, we know it's normal. Then you can apply in R all the calculations like pnorm, qnorm. In Excel, it will be norm.dist, norm.inv to find the area given the axis like 2.3, or the other way around. Given the area, find the axis number to find the inverse norm. So all these are becoming a lot easier. Let's imagine this. Suppose n is 3, right? Or CLT cannot be applied, or CLT doesn't exist. So we have this very weird shape, non-normal sampling distribution of sample. So what are we going to do? No choice. We have to compute like this to generate the full distribution. Then we can perform some lookup or basically repeat counts. Repeat counts can be done manually, and even in computer, that is very quick and very fast. We all know that. Repetitions and adding up one by one is no big deal. But it's big deal if you're going to do massive data analytics, right? You're not going to do this one time. You're going to do this gazillion times. So if one such count or measurement or computation takes 1 second, then performing analytics, animations, visualizations gazillion times will take gazillion seconds, and that's the end of universe. Not viable. But then if doing this normal calculations, and it's now very well known, it can be done in very, very short amount of time, then you can do a big data kind of analytical calculations, visualizations, simulations, very it empowers you, right, and software developers to perform this calculation repeatedly in a massive way without degrading the computing performance. So that's the key to getting a lot of things done when we apply such theorem to our analysis here. So that is the case when we don't have normal parents. What if we have normal parents, right? So in short, we want to have a takeaway. We want to say that by CLT, right? So parent not normal. So parent not normal. Not normal. But n is large. Right? Then we will apply CLT to ensure that sampling distribution of sample mean is going to be normal. And again, this is a theoretical result, seemingly quite useless as if, but actually it's very useful because then once we have this as a theoretical basis, we are empowered. Now we get the license to apply P norm, Q norm in R to do quick computations based on this result. And we don't have to worry about, oh no, this is there's a lot of leak. It's really not. How can you approximate a 3-point distribution with normal distribution? That's going to be very inaccurate, right? Even though your computation is fast, it's very quickly inaccurate, and that's not the point. Yeah. So thanks to CLT, we can apply P norm, Q norm. And what happens when we have normal situation? So now let's look at the other case, which is way easier. Okay, so now suppose our little town here of 100,000, but we can divide by 200,000. So we get a 0.5, 0.5. That becomes a probability distribution. In fact, it becomes a Bernoulli distribution, right? Half the time it is 2, half the time is 3. So what if we don't have what is that? What we don't have a discrete case like this. What if we now allow for any amounts of money in the wallet? Okay, any amounts between 2 and 3, with the bit of relaxation that, well, there's a small chance, right? So we allow for a small leak, small chance for the town people to have amounts larger than $3. Okay, so now they are printing coins and fractional coins, 1-cent coins and all this, and occasionally, but very, very unlikely, it's like one person out of the 200,000, right, carries $3.50, $4, $5, and no one has $100, something like that. Okay, so if it is normal, so that means we start off with as x follows normal. Okay, and of course for normal we know very well it has to be 2.3, 2.5. We know it already, yeah, because it's normal. We know that. So everything is quite known about normal. That's great. And furthermore, it's not just calculation, but mathematically, normality has a lot of properties. Has a lot of properties that are attractive in terms of mathematical analysis. So for hypothesis testing, for chi-square test, for F-test, and all these, they all assume normality in the parent distribution. So it's good that we can have a normal distribution in the parent. So if we have normal distributions, then one thing to note is normal plus normal results in a normal distribution. Right. So if we do the averaging, we just perform a fraction. Example, a fraction of normal gives rise to another normal distribution. In other words, so remember these are pictures, right? So we have a picture, a normal plus a normal gives rise to another, perhaps slightly differently shaped normal curve, but it's normal. So maybe the mean is shifted, right, to the right, the variance will be, that means the shape may be a bit flatter, but nevertheless, it conforms to all normal distributions requirement. A fraction of it, if you multiply it two times the normal curve, you make 2.5 become 5, right? You make 2 become 4. So kind of like a bit differently stretched. So a stretched normal, fortunately, we can prove it is still normal. So these properties allow us to then conclude that when we perform sampling distribution of sample means, we are adding up normal curves, then multiplying by 1 over n. And that automatically guarantees that the sampling distribution of sample mean will be normally distributed. As to how to show these, well, it's hairy. You have to really go down to all the PDFs and stuff to prove very rigidly that this works for all kinds of normal distributions. But let's just take it as true first. If these two are true, then sampling distribution of sample mean basically means that you randomly pick from x, you randomly pick from x, you randomly pick from x n times, and you keep adding them up, because to do this averaging means you add them up, then divide by n. Yeah, adding them will result in a normal distribution. Dividing by n, right, is like multiplying by 1 over n, because a is any number, real number. So that would still keep it as normal distribution. And therefore, we can straight away, all right, conclude that when n is n, yeah, we will get normal distribution. Well, it's a lot stricter here, so I need to try to limit it to 2 and 3. So okay, that's our xn here. And remember, the reason why we need CLT is to make sure that our software, our calculation, we can use P norm, Q norm, right, to find the probability, or to find the inverse probability for various uses like hypothesis testing, finding critical values, finding confidence intervals. So we prefer, we hope for our xn to be normal. And when we didn't start with a normal parent, we are able to get normal sampling distribution if n is large. Yeah. And in the case where we are fortunate enough, we start with a beautiful normal parent, right? Then automatically, we don't have to say applying CLT or whatever. And whether for sample size large or sample size small, even for 2, for example, we will get normal distribution. All right. Okay, so that's the whole idea. And of course, x2 bar is already following normal. And so xn automatically follows normal. There's no need to apply anything. So that's the big idea behind. And we can therefore say that in conclusion, so let's do the same marking here. Normal, right? Normal. Starting off, we are lucky. Sometimes in real life, it's about not lucky, because normal, the perfect normal is never existing in nature, because normal distribution is a mathematically constructed creature. So real life measurements tend to look like normal, but they will cut off. They will have a hard cutoff, right? Typically at 0, for example, income distribution looks like normal, but then nobody has negative income, right? So in that case, that kind of measurements, they will have a hard stop at 0. And if there's a minimum wage, then there will be hard stop at $100 or $200 or whatever it is. And how can you say that is normal, right? But then if it looks already very much like a bell curve, then we just ignore that little bit of inaccuracy at the edges and just say, hey, you know what? Assume that income is normally distributed. And sometimes the word is not even used. The assumption word, the assumed word is not being used. It's just saying, since income follows normal distribution, our sampling distribution of sample mean will be normally distributed, right? So that's why it may add to the confusion. So by these properties, right, by these properties, we will already know that xn, well, I should use back the same color. Whether n is small or large. That means it's very robust, right? It doesn't matter whether n is small or large, whether you do a lot of hard work or not. Okay, so automatically. Okay. So lesson learned here is that I like to remember this more like a kind of a small story to remember what's going on, right? So if parents are normal, then the children are normal. If parents are not normal, then if you do a lot of hard work, then the child distribution, the sampling distribution of sample mean will be normal. So but kind of an easier way to remember, if normal means beautiful, beautiful parents produce beautiful child. Well, not beautiful parents, right? Ugly parents, if you try hard enough, large sample size, you will be able to produce beautiful child. Of course, it's just a joke to try to remember this very real mathematical behavior, right, of sampling. Now, just one more word to add about the parameters within the normal distribution itself. So typically, so this is an illustration with the $2, $3 dollar notes in the town people. But typically, we will talk about sampling distribution of sample mean, right? Being constructed out of sampling from the parent. Yeah, okay. I pick a number from the parent. So the parent can be this, can be this. So I pick a number 2, or I pick a number 2.5. Remember, this is continuous, right? So I pick a number 2. I pick a number and I just label it as I need to label it as bracket 1. That means the first time. So that's different from the sampling distribution. Bracket 1, the first time. Then I randomly pick another person, right? That is from the same parent, right? That's from the same parent. And so it's from the same distribution. But I want to note it as the second instance, right, from the same parent distribution. And then I pick the third parent and fourth parent. So in this case, if I pick only 2, then what happens? Well, I want to, this is the sampling distribution of sample mean. So I want to take 1/2 here. Okay, remember all these x1, x2, or x bracket k, they all follow normal distribution with a mean of mu and sigma. Sorry, they all have a mean of That's one thing about writing. Okay, so I need to erase that. So the mean, let's say they all have the same mean. So in this case, it's 2.5, right? 2.5. But I'm going to generalize it to mu. And the variance of all the xk's, we'll call it sigma squared. Okay, so what happens then? Nothing happens. We can't do much unless we know the distributions of x1, x2. Then we have to go into details. But that's not my point of talking about that. I want to talk about the expected value of the sampling distribution of sample mean. Yeah, and so when we do that, then that just means expected value of half of the first measurement from the parent and the second measurement from the parent, right? And that is the average, right? Expected value of this. That means what is the mean of the means? What's the expected value of the sampling distribution of sample means? So in this case, then we convert this into mu and convert this into mu. And remember, for expected value, we can bring out the half, right? Okay, but we are going to see that first of all, we bring out the half to get E of x of 1 plus E of x of 2. Now, I should not confuse you with this here, but mu is this expected value, isn't it? Because when we say mean of xk is mu, that just means expected value. Yeah, so the E of xk, any k, 1, 2, 3, 4, 5 is mu. So this means this bracket is mu. This E of x bracket 2 also is mu. So 2 mu divided by 2, essentially it just means mu. Make sense? Now what happens if we talk about the variance of x 2? I should then change it to 2 because I stopped at 2, yeah? So it's easier that way, yeah? So variance of x2 bar or x bar 2 will be the variance of half of x1 plus x2 bracket, right? Now remember that when we bring out the constant, we can first split them. So let's just talk about that. So variance, we can take out the constant, and that would give us 1/4 because we're going to square the half, and that leaves us with variance of x1 plus variance of x2. And assuming x1, x2, they are independent. Actually, with finite population, it will be not independent, because imagine there are only 2 people, not 100,000 people, right? If there are only 2 people, if I pick the first one who is having a wallet size of $2, then it guarantees that my second pick, it will never be 2, correct or not? So it will be very dependent on what is my first pick. If it is 3, then it will guarantee that my next pick will never be 3. So, but then for large size, population size, that's why I give 100,000 people, right? Or 1 million people, or 10 million people. It's not infinity, but it's large enough to ensure that the effect is not so drastic, right? So they can just be assumed to be independent, and so we don't have to worry about that. Then we basically get variance of x1 bracket, and we split that, right? Variance of x2 bracket. Now notice that this is actually our sigma squared because they are the same. Remember, because for xk, whether k is 1, 2, 3, 4, 5, they all share the same variance because we're drawing it from the same town, from the same population. And the distribution of the parent is, the distribution is the same. The individual wallet number may be different, but as a collective, that town is that town. That town's distribution is the same. So that's why the variance of the town, right, of that population is the same. So now what do we have? We have 1/4 of 2 sigma squared. So that is going to be half sigma squared. This 2 is related to this 2, as you can trace through. Okay, and well, in general, we can then see that if we are not dealing with 2, but we are dealing with n in general, right? So whether n is big or small, it will be 1 over n of x1, x2, plus all the way to xn. Can you see this? Okay. And it's just extending this to xn, that's all. Yeah. And this is a number, like 2 here. And we can do this, I don't have to expand this all over again and mess up my very precious paper real estate here. But you can just see that, just add some more until xn, and this becomes n. We bring out the n, yeah, and it will be basically the expected value of x and x bar n is going to be 1 over n of mu plus mu plus mu n times. Just to write in English easier. So n mu divided by n, we get back mu. So what is this all about? It's trying to say that whether you pick sample size of 2, 3, 4, 5, 30, 50, 100, 1000, whether sample size is big or small, the mean of all the means is going to be the same as the population mean. Remember, we are trying to look for this number. So the important thing is this side, on the right side, not observable, not knowable. We don't know it. We cannot know it. We want to know, but we cannot know. This side, all right, is observable. We can see it. We can feel it. We can calculate it. That's the main difference. So this derivation, the significance is not, after one whole calculation mess, end up it's just the same as mu. So what's the big deal about it? The big deal is our intuition that to estimate the whole town's wallet average, we could try to just average 2 persons next door or random people, ask for their wallet amounts, take the average, and that number, even though is not going to be exactly accurate, is a good estimate, right? Our intuition is that. But how to prove it? This is the proof of that. You expected values means as you repeat this many, many times, as n gets larger and larger, right? In both sense, you will expect to find that your activity, your observable activity, will become mu if you do that infinitely many times. And if you don't do infinitely many times, as in real life, then it will approximate mu. So it's good to get this equality result. Right? That's the significance. And for the variance, we can just again repeat everything above to find that it is taking out the 1 over n, right? Variance of 1 over n. So we get it as 1 over n squared. So once you take out the 1 over n. And this will be variance of x1, x2, x3, x4. So we have sigma square, n times. Can follow, right? Because of the 2 example, n equals to 2 example on top. And what happens then is that we are basically saying 1 over n square of n times of sigma square gives rise to sigma square over n. Now, this n here is the necessary result that is introduced by our calculation of the variance of sampling distribution of sample mean for n equals to n, for sample size n. It is not the definition of variance. The definition of variance has a 1 over n multiplier there as well, right? That is already embedded inside. This n is not due to the definition. So in other words, to find sigma square, you have to measure the values of x, k, right? Measure all the values, all of them, everyone's wallet, give me, right? So 2, 2, 2, 2, 3, 3, 2, 2, 3, 2, 3. And you find the mean, then you find the differences from the mean, right? So 2 minus 2.5 squared, 3 minus 2.5 squared, and you find the square of all the differences from the mean, add these squared differences up, and then divide by n. So that divide by n is done in the sigma square. Inside, if you go inside the micro universe of sigma square, then you'll find that there is a divide by n due to the averaging of the squared differences from the mean. But then this divide by n is additional divide by n. That's oftentimes the confusion by a lot of students. Whether you are high school, tertiary, or whatever it is, you learn already, later on you get confused again. And that this over n here, when we perform sampling distribution of sample mean, there's a bar here. Yeah. So this bar here, should you try to find the variance of this x bar, you will have to divide by n due to this derivation, right? There's no running away. It's a very required, rigid step. And if you don't divide by n because you say, well, earlier on in sigma square already divided by n. If you do that, then you are really going to get into big trouble because your variance will be wrong. So this is after getting the sigma square, then divide by n. So if you do have to calculate sigma square, you find that you have to divide by n. So that's a separate thing. But after doing that, then you again divide by n to get the variance. So here, what is the significance? This is telling us as n goes larger, becomes larger and larger, right? The variance of the xn bar becomes smaller and smaller, which is good thing, because it means that the precision or reliability increases of the precision, the estimate. When we use the sample mean as a point estimate, remember the declaration, right? The assertion without proof. I take the average of my two neighbors, 1.6 meters, and I claim that this is the population average. This is the average height of all people in this statistical town of 200,000 people, right? So that's a very daring assertion, right? So people will challenge me and say, are you sure or not? Yeah. One big challenge, one easy challenge for anyone to try to dispute my claim is to say, but your sample size n is 2, right? So to mock at my small sample size n is definitely a valid way to attack any claim, any assertion. So now that you are learned in this area, you can challenge other people, right? And if you should see that n for that claim is small, then you have a valid argument to dispute. For example, if in the COVID-19 days, the pharmaceutical company says, yeah, we have done our due diligence, we have done clinical trials, and the average result is very good, 92% efficient recovery, whatever that means medically. Then the government might challenge the pharmaceutical company. What's your sample size? We did it on 2 patients. Right? Okay, good. Now we dispute the company's claim that their new drug, COVID-19 drug, is reliable, is providing good vaccination or whatever. Why? Because sample size is 2. The company might say, do you know it's very hard to find people who will volunteer? That's why sample size 2 is already the best. But then it is valid to challenge a small sample size. Difficulty we can understand, appreciate, and maybe work around. But you cannot accept the end result as valid. In other words, the final result of this 92% or whatever they say is efficient due to sample size of 2, because that's the sampling distribution of sample mean of the efficiency, right, or the effectiveness of the new drug, right? That point estimate is not good enough. It's not reliable enough to estimate the actual efficiency. Maybe the new drug's actual mean efficiency, if you apply the new drug to 100,000 people, 1 million people, maybe the average efficiency is just 70%, or even 50%. And then kind of by chance, they pick 2 very strong patients. Volunteering patients, typically they're already mentally prepared. They know they are good. They know they can withstand whatever unexpected situations and conditions. So generally, maybe their body is healthier. I'm finding excuses and possible reasons. The thing is, the main point is, sample size 2, you can get any 2 very good, very bad. Of course, pharmacy will, companies will pick the 2 very good ones, right, and then claim as random, and so on. So when sample size is small, one needs to become a bit on the alert, on the suspicious side. And that's why you learn statistics, right? You want to learn statistics to become a more discerning consumer, to become a more discerning decision maker. Should I take this vaccine from this company who has an N equals to 2? Or should I take the vaccine from another company who has an N equals to 200? Right? And so this kind of analysis and understanding will give us a much better confidence, much greater, belief in our own decision-making process. And as a company, as an organization, as a government even, when you go by data analytics based on statistical theories, right, that the proof, the science, the mathematics, the theories are all behind you, and that is far better than any single person trying to say, no, I think I feel, right, and that's just a claim. So if we go by hard data, then we need to process the hard data the theoretical way, and all these are good guidance, right? As we understand the formula now, as we understand the implications just purely due to mathematics, we can then kind of raise this inference, this understanding to a higher level, and say that, well, with greater precision and greater reliability due to higher sample size and because variance is narrower, right? And therefore we can feel that our decision is right by picking the drug company that has done a clinical trial over 200 patients, even though their effectiveness is 88%, right? But I believe their numbers more than the other company who did it on N equals to 2, and they claim that their effectiveness is 99%. I don't think so, right? Something like that. Okay, so this is just to enhance the quality of our decision-making process. So hopefully by now you can see how these 2 main points that we started off trying to discuss, the sampling activity and the central limit theorem, how they interact with each other based on the goal of trying to find mu and the behavior of the given parent distributions themselves, something we cannot control, by tuning the sample size, something we can control. And after tuning the sample size to a level that we can afford, we need to interpret those measurements and the sample means on the sampling distribution of sample means, not on the original parent distribution. Okay, that's all I have to say for this session. Thank you and see you in the next video.